Hi, everybody. We might as well go ahead and get this rolling. Please go right ahead and get your beverages and have a seat. I'm Ren Herman. I'm with the Creative District, and I just want to say welcome to everyone. We're delighted that you could join us this evening for Science on Tap. And I'd like to introduce Linda, who's going to just tell us a little bit about our speaker this evening. Thank you.
So hi, my name is Linda Anderman. I do communications over at the Bradbury. And as Rick said, this event, which is the third Thursday of every month, is co-sponsored between the Creative District and the Bradbury. Our topics are always science, although there are some other ones that happen during the month. It's always right here. Feel free to get up and get things to drink. We thank very much Uncork for hosting us here every month. I will tell you that the one for next month, I don't have a title, and she's still figuring out exactly what she wants to talk about, but it is a woman from the laboratory who works for our inorganic isotope and actinide chemistry group. Woo! And her name is Sharon Bone, and this will actually be sponsored next month by the American Chemical Society, so we will have some free food and drinks if you needed an incentive to come.
Yay!
Yay, chemicals. Yay! So for our speaker tonight, so the topic is, what's shocking about lightning? And we actually advertised both Tess Light and Tim Hamlin, but Tim had to go away. So we'll support her extra specially because she's here by herself. Yay! So Tess Light holds a PhD in astrophysics from the University of Minnesota. In the 1990s, she was a Fulbright Scholar at the Australia Telescope National Facility, a postdoctoral fellow at the Canadian National Research Council, and a Lannell Director's postdoctoral fellow. But there's more. Tess came to the lab to work on Forte, which is a small satellite, and on that team studying lightning as a demonstration of next-generation nuclear detonation detection technologies. She began working in the U.S. Nuclear Detonation Detection System program in the 2000s and has served as a chief scientist under the, I don't know what this acronym is. It's USNDS.
United States Nuclear Detonation Detection System.
EPM.
EMP.
EMP.
Typo if it says EMP.
Oh, sorry. I'm the typo. Sensor development effort at the lab since 2011. In 2016, she became the chief scientist for the Space-Based Nuclear Detonation Detection Program at the lab, as well as a project leader for on-orbit EMP analysis and operation. Her specific expertise includes Monte Carlo simulation techniques, digital signal processing, statistical analysis, end-to-end system modeling, and optical and VHF signal propagation physics. Next month we'll try and have somebody with more experience. But please welcome Tess Light.
So, I don't think I need that. I can talk pretty loud. But I do need this because I can talk pretty long. Okay. So I put together, I'm trying to give a narrative flow about lightning, okay? Lightning's pretty cool, and one of the things that's cool about it is that we don't understand it very well, and you would think, given that it strikes the ground something like 40 times a second, 50 times a second worldwide, and has since the dawn of time, we would understand it. But we don't, not perfectly. And so that's pretty interesting that there's something so common that we still don't quite physically understand. So that's one of the reasons we study lightning. And as was mentioned, the reason we study it here at the lab is because the signatures that come from lightning, the light and the radio waves that come from lightning look a lot like what a nuclear bomb gives off, and we like things that explode at the lab. So if we want to detect a bomb, we can train our sensors on lightning. So that's why we study it. So just a couple, a little bit of a reminder about some physical things, because I'm going to say these words a lot, so just so we're all on the same page. So you know, an electron is a little tiny unit of negative charge, and a molecule is a clump of atoms or whatever, and it's usually neutrally charged, but if you strip an electron off of it, now it has a net positive charge. Okay, so we've got negative charges and positive charges. And a current is any time the charge is moving. So if you have a net flow of electrons, you have a current. So that's, there's charges and there's currents. Charge always has to be conserved. You can move it around, you can add a positive and negative to get a neutral, you can do whatever you want with it, but it's always conserved. And if a charge is sitting there, just hanging out, having a glass of wine, it's going to create an electric field. Just a static electric field is going to be around that charge. But if the charge is moving, okay, now you have a current, and if it changes something about how it's moving, so it speeds up or it slows down or it starts and it stops, anything about that is going to create radiation, that comes off of it, electromagnetic waves, not the kind that ionizes you for an X-ray, but like radio waves. Okay. So now, also, what's a capacitor? A capacitor is where in an electric circuit you've got a little element that is holding the charge. It's not letting the charge flow. Okay. And a capacitor is designed so that at some point you get enough charge built up, you get enough energy in there that it breaks down whatever's between the two little plates of the capacitor, cause a little breakdown, tiny little spark, and now the charge, you can get a current to flow in your system. So that's what a capacitor is. But that's also what the Earth is, because there's a global electrical circuit on the Earth. There is, even when there's no thunderstorms or anything, there's a small fair weather field that's always existing in the atmosphere. Now, if there were nothing driving that current, if there was nothing keeping that current going, it would be gone in a few hours. It's like there's a lossy capacitor between the Earth and the atmosphere. So it's just like an electric circuit, but there's something driving it. We it's not clear exactly what that is, except everyone suspects that it's probably thunderstorms. So thunderstorms are continually charging up the atmosphere to keep this electric current going. There's also things hitting from the solar system. There's charged particles hitting from the solar system. But the main driver is thunderstorms and electrical activity in the clouds. But how did we get the electrical activity in the clouds in the first place? So this is one of the first mysteries about lightning, is that it's not perfectly understood how we even get the charge up there. Okay, so I'm going to try to walk through this and be clear, but if I'm not, please interrupt me. The leading theory right now goes as follows. You have a thunderstorm forming because it's a hot day and the ground heats up and the air convects upwards from the hot earth, and you get these towers of convection, okay? And that creates the thunderheads that you're used to seeing, very tall clouds that are forming. And that's because the air is literally, there's a very strong updraft. And the warm air rises and it cools down and it comes down on the side. So you've got a big convective cell. And while that's happening, there's all these particles in the cloud. You've got water, you've got tiny little ice crystals, you've got hail, you've also got something called graupel. That's that soft hail that you'll see. It looks like chunky snow or real small soft hail. It's called graupel. And so the leading theory right now is that mainly the graupel and the ice, they're banging into each other because of this convection. And when they do that, they exchange a charge. So the graupel, say, gets a negative charge and it's heavy, so it doesn't go up as high in the convection. And the ice now has a positive charge because it gave one of its electrons away. But it gets lofted really high. And this keeps happening, and you end up with this layer of negatively charged stuff with a layer of positively charged stuff above it. Except that we also see lightning sometimes in clouds that don't seem to have any ice. So it's not perfect. So there's some questions, okay? And except that, many times we see clouds that have that nice main negative layer and a positive layer above it and another positive layer below it. So that's not explained by this model either. And this model is very dependent on the tiny little changes in the temperature as to whether graupel's going to take a negative charge or, give a negative charge. So it's not perfectly understood, and I can't explain it to you because it's not perfectly understood. It's a whole field of study on its own. But that's happening. So somehow magic occurs and we get layers of charge in the cloud. And a typical cloud is going to have this like a positive layer, positive charge, and a big, thick negative layer. And it's usually the negative layer is around somewhere between 0 degrees Celsius and negative 10 or 20 degrees Celsius. So there's a temperature dependence. And then there's a positive layer above it. And so, for example, in New Mexico, where we're at a very high altitude, that temperature of 0 degrees Celsius occurs closer to the ground than it would over, say, Florida, okay? But it's sort of the same height in the atmosphere, but it's closer to the ground. And in winter, it happens lower in the atmosphere because everything's colder. So depending on what part of land you're over, whether it's winter or summer, whatever, lightning seems to have a bunch of different characteristics because it's not just temperature, it's also air density and all sorts of things. And so when I say typical a lot, that's because pick anything that I say, and the opposite also happens. Okay? So a typical charge would be a positive layer on the bottom and a negative one and then a positive one. But we see the perfect inversion of that too. We see storms that have just 2 layers, and we see them in either direction. So anything pretty much happens. And that's why it's so hard to pin down exactly what's going on, because it's just, you can find observations that refute or confirm, a lot of different things. So it's a little tricky. So that's how it charges up. But now we're going to talk about the lightning itself. And now, big surprise, how the lightning actually happens is also something of a mystery. And people are so I'm neutral. But there's some people that are pretty, and they're right here in town, so they're pretty invested in this, okay? Here's the problem. It's, again, like a capacitor. We have 2 charge layers in the cloud. And so a spark happens between them, and you think, well, that's easy enough, right? I mean, I walk up to the doorknob and I touch it and I get a spark. So something broke down that little tiny air gap. I had a big enough electric field, just like my capacitor. I get a big enough electric field that it breaks the air down in between, and a current can flow. Because air is normally an insulator. But you have to break it down. If you put a big enough electric field, you'll break it down. Sounds pretty easy. Except that never have we observed in a thunderstorm an electric field anywhere near what is required to break the air down. So in fact, it's off by at least a factor of 10. So it's not like we're kind of there. We're not there at all. We don't see it. So something else is happening. In lightning, of course, we cannot command it necessarily. We cannot do a controlled experiment over many kilometers, volume. We can't force it to our will, so we can't be in the right place at the right time. But a lot of research has been done trying to find super enhanced electric fields in the clouds to explain why air suddenly conducts electricity, and we can't find it. And we're all very glad that air doesn't conduct electricity, because life would be pretty dangerous if it did. Well, it's true. Andy's laughing, but it's true. That's confusing. So one of the leading theories for how lightning starts is that there's cosmic rays. They're hitting the Earth, the atmosphere all the time. They're very high energy particles from all over the galaxy, black holes, supernova, everything. They're emitting these high energy particles. They hit the atmosphere, and when they come through the atmosphere, they strip electrons off of the air molecules. And now you've got these free electrons floating, which is kind of like a current. It means the air is predisposed. It can allow a current to flow now. So it shouldn't take nearly such a big electric field to just cause the air to spontaneously break down. And that sounds pretty good. And one of the fathers of that theory is Bob Roussel-Dupré, who retired from the lab several years ago. Maybe some of you know him. But now, another guy at the lab named Xuanmin Shao, recently working with New Mexico Tech, who has a very vibrant lightning physics group. They have made some really cool observations, and I can talk about observations in a minute, but they made some really cool observations of detailed movements of charge in lightning. And they're seeing that most, possibly all lightning discharges seem to arise from an initial spark that's very small, spatially small. It's only over meters. Lightning ultimately ends up being, many kilometers long, but it starts very small. The cosmic ray theory would require a very long, many kilometers of buildup of the electrons being stripped off in the atmosphere. So my cosmic ray knocks off some electrons, then they knock off some, they bring two friends, and they tell two friends, and you get like a big shower of electrons. And that occurs over kilometers. But lightning seems to be starting in a very small region. So those observations are in direct contradiction to the cosmic ray theory. Also, we see something which I think is really interesting, and I don't think the cosmic ray theory quite explains. The way lightning happens when it happens is it doesn't happen, your eye perceives a huge big bolt, but what actually is happening is a gazillion little, we call them steps, so little steps of discharge, little current flow over small spatial, little tiny steps, and they're trying to find their way to ground. It's attracted to the ground because charge can dump into the ground, and it's being sort of moving that way like water. But if you think of water flowing off a mountain, and it goes in many different paths, looking for the path that's going to lead it to the ocean, and eventually you get a river. But there's all these little, like in a river delta, you have all these little branches that come off of it where water thought it could go this way and found out that it couldn't. Other water thought it could go this way. Same kind of thing. The charge is trying to come down, creates that branching structure, and only finally one lucky channel makes it to ground. So those are called streamers. The steps create these little streamers, the branches. Coming up from the ground, we also see streamers. So as the lightning is coming from the cloud towards the ground is causing a tiny little lightning coming up. There's this enhanced electric field under the storm. That's what you feel when the hair stands up on the back of your neck. And that's causing a break. You look horrified. There's streamers coming up from the ground, and when they attach, so the lightning doesn't actually strike the ground exactly. It strikes a streamer that's rising to meet it. And in a really fast camera, you can sometimes catch the streamer, the upward, the connection streamer. So that's cloud to ground lightning. You can also get lightning between the charge layers in the cloud. So there's a lot of lightning that occurs in the cloud, and sometimes you'll hear thunder and see the cloud light up, and that's lightning, just connections between the charge layers. And you can get one cloud, something leaping out of it and hitting another charge layer over in another cloud, and it extends in the cloud. You see a lightning strike to ground, but typically that's only about a third of the lightning that occurs. The majority is this stuff in the cloud, and every time it hits the ground, it spreads out. The charge motions and the discharges are spreading out through the cloud horizontally too, for tens of kilometers. This is why when they say when thunder roars, go indoors, because the cloud is huge, but the lightning, maybe the strikes are 20 kilometers away over there, but the electrical circuit that is part of can be over you. And there's no reason it can't come down over here just as easily. So that's where that comes from. So what do we observe from lightning? We can observe the light. So the air, when the current finally flows, it breaks down somehow. The charge, we get a charge layer in the cloud somehow. Then the air breaks down somehow. And then the current lights up a channel, and we actually know how that happens. So that is simple. When you heat something enough, it glows, okay? And so the air is like the tungsten wire in your light bulb, and it glows at a characteristic color, which is white. It's white hot. In fact, the temperature of a lightning strike is around 25 or 30,000 degrees Celsius, which is about 4 or 5 times hotter than the visible corona of the sun. So for a very brief moment, we've got something super, super hot, and it makes the air glow. In addition to the glowing, just because it's hot, you see transmission lines from molecules in the air. So you'll see characteristic lines like nitrogen and oxygen and stuff. And those are like your fluorescent neon signs, give off a characteristic color depending on what gas is in there. So this is like on top of that white hot glow, there are actually even brighter bits at certain frequencies that are because of the molecules in the air. And so there's light. There's thunder, which is the superheating of the air when this, this breakdown current happens, and you get basically an explosion, a shock, and it superheats the air, and you get a shock. and there's a big bang and you hear it. The electric field, so the electric field is building up and building up and building up. Like I said, never as high as we want it, but it is building up. And then when you get a discharge, it tends to restore things to where it was supposed to be. And so we can measure the electric field, and in a storm you'll see it going up and up and up, and then when there's a discharge, maybe it drops, and then it builds up again and it drops. And you can also measure the changes when the super fast time in that exact moment when the E field changes, you get a little pulse. When the electric field changes fast like that, that's when you get radiated, like electromagnetic waves, radio waves. And if you go listen to your radio when a thunderstorm is nearby, you hear a lot of static. That's literally from the thunderstorm. It's